Welcome to this afternoon session of this low-code workshop. This afternoon we have three exciting talks. In the morning we had talks by the industry. Now we have presentations by academics, and they will present interesting methods and techniques and experiences on different scalability issues and aspects that could be integrated in low-code development environments. So the first talk will be by Antonio Garmendia from the University of Linz in Austria, and the title will be Design of Scalable Domain-Specific Modeling Languages. As a reminder, the talks are about 40 minutes, so one idea is to have 30 minutes for the presentation and then 10 minutes for questions. You can ask your questions if you are here in the Zoom meeting. Please use the chat, or even better, use your mic. If you are watching this from YouTube, you can use the YouTube chat, and in any case, you can also use Twitter. So maybe, Antonio, if you can try to share your screen.
Yes, working on it. Yeah, so yeah, you can see my screen, right? Let's see. Yeah, thank you, Juan. May I start?
Yes.
Oh, great. So, welcome everyone. Thanks, Juan, for the introductions. Indeed, I'm working now with the JKU Eclipse University. Thanks to everyone for attending to this talk, which is about the design of a scalable domain-specific modeling languages. So, in this talk, I will start with an introduction to model-driven engineering, specifically the challenge when designing domain-specific modeling languages. After this, I'm going to explain the approach that we decided to design those languages in the modularity way. And after this, and the creation of the graphical concrete syntax in DSML. After this, the application of this approach with some case studies, and finally some summary of the talk. So model-driven engineering basically promotes a model-centric approach for software development. So therefore, models plays an essential role in the MDE. So in the MDE, basically, we have two principles. The first one is to increase the abstraction, and increase the abstraction. We do this creating the domain-specific modeling languages in which we isolated the developers from the complexity and reduce the effort in developing a certain application. And the second principle is to increase in the automation, in the sense that we have those creating models using the domain-specific modeling languages, and to immediately generate code from for a specific platform. So how we usually create these domain-specific modeling languages? So the creation of these DSMLs are recurring in MDE, and usually we create an abstract syntax, concrete syntax, and the semantics. Usually, to describe an abstract syntax, we describe it using a meta model. So this is a meta model for an excerpt of a telecommunication. We say that meta model has a class home and includes a one cable model, and we should create models that conform to this meta model, say like home, and have this scalable model with this IP. And to create these models, usually we design a suitable modeling environment, which is to have a canvas and a palette to facilitate the creation of elements and the relation between them. So, but there exist some challenges when designing those environments. So, for instance, those environments are characterized by the use of monolithic models. So, in practice, in MDE, the construction of monolithic models may become large and wild, and when that kind of things happen, so the the tools they become it will be very difficult for the tools to process those kind of models. So we have an approach which is a pattern-based approach for this language modularity. So the other challenge is regarding the graphical editors. Usually building modeling editor is expensive, and since they must adapt to the particularity of the modeling language, so for which the editor is defined. So building of graphical languages is particularly challenges if the construction typically requires deep knowledge of the language development framework. So then we would like to isolate the developers of this complexity, and also we would like to fragment, of course, the concrete system in the sense that we can improve the scalability and the separation of concerns. So in this sense, we have an approach which is a systematic engineering of graphical modeling environment. So let's start by an approach for the language modularity. In this sense, I'm going to propose this pattern-based approach, first identifying some requirements that a scalable modeling environment should have, an approach to build those environments, and based on the requirements, we design the base of patterns we mentioned that the catalog of modularity patterns to fulfill those requirements. And after that, I'm going to propose our tool, which is we called it EMF-Splitter. So from our point of view, a scalable modeling environment to have several characteristics, in the sense that the first one is the ability to define fragmentation strategy for models, in the sense that we don't have all our models or our objects in just one model, just to try to enforce the separation of concern in order to improve the performance, in the sense that our tools doesn't have to load all the objects, all the model at the same time, just basically it will be enough for a pilot fit. So also the ability of organize the model content hierarchical. So in the sense that we have our models separated by packages, folders, and try to improve the usability. The third one is the ability to control the visibility of elements. Now that we have our element fragmented, split it through the file system, we'd like to define the visibility of those objects. So it's like basically in programming language, we define that one object is public or private. And also the scope of the cross references, in the sense that when I'm going to would like to find a candidate object, then just define in which are the objects that are candidate for to reference with. And the fourth thing is to try to the ability to customize the scope of the theoretic constraints. So usually when you have a meta model, you attach OCL constraints and to for validate those models. So basically we would like to scope this in theoretic constraint because we have now our model splitted. So maybe the constraints doesn't need to load the entire model to execute the constraints. So try to design to improve the performance. And finally, the ability to define model indices. So we will have like a backend, maybe SQL database or NoSQL database, in which we have some indices to so that we can improve the constraint execution. So our approach to build these modeling environments is the process is basically in this figure. It shows our approach to design these scalable environments. So this approach provides a catalog of patterns that we can define these patterns at the meta model level. We can define this as many patterns as we like, and with the information of this pattern, we can generate automatically a modeling environment in which the users can create model in a fragmented way. So how we can define the pattern at the meta model level? So in this sense, we're going to use a synthetic example that basically a pattern is like a meta model. And the classes, the reference and attributes are called roles, and each roles can have a cardinality. So the cardinality rules how many times the roles can occur in a pattern application. So to simplify this, we have this pattern that has two class roles and one attribute role and one configuration role and this reference role. So this role doesn't have the cardinality, so we suppose that this we can instantiate it just one to one. And the other one, this class role and this reference, we can instantiate it one to many. So we can instantiate a pattern using this domain meta model, and this is the pattern instantiated. We instantiate the row A one time, so we can just instantiate one because it has no cardinality. And we can instantiate the row B just two times, just with class B and with class B1 and B2. And the result is in this figure, in the sense that our class B is role B, this class B2 is role B also the reference as role ref, and I give it as this attribute configuration a value, which is val. So throughout this presentation, I'm going to use this example of wind turbines. That was one of the case studies we worked on in the European project called Mondo. This language defines a class of WT components which include a set of subsystems. So this set of subsystems, we can define different components. Basically, we can define the input and output that we can connect it using a connector, and a control subsystem can define different kind of state machines. Right? We can connect components to state machines also with these different states. So how we define our model fragmentation pattern. So the fragmentation strategy should be specified at the metamodel level, where the different classes can be titled as project, package, and unit. So we take inspiration from the modularity concept of languages like Java and its Java development tools, JDT. So similar to JDT, we are able to select a class that's going to be the project, and the project is going to be the root in which we can contain the rest of the elements, which can be any of the other types, package and units. So inside the package, you can contain objects of type package directly, and you can contain units as well. So in the units can be defined either inside a package or directly inside a project. And the units are going to group all the related, basically all the related elements. So how we apply this model fragmentation to this WT components meta model. So this is a fragmentation pattern defined as a meta model. So we should define at least one project and one unit, and it is optional to define a class as a package. So in this WT component, we define the WT component class is a project, and we define two packages and two units. The package system, you have different files that are going to be the architecture, and the package control systems, which is a class that's going to have several files of state machines. We also define some values like the icon and the extension for the unit. So based on this model fragmentation, now we define the reference scoping pattern. The reference scoping pattern basically is for define the set where when you have the reference for class A and class B, we would like to get as a result the objects that are going to be candidate to be references. So for doing this, we created this scoping pattern and with different type of scoping. Like you can say that I'm going to search the object in the same workspace, the same project, the same root package, the same package, and in the same unit also. So in this example, we used also the WT meta model. We applied the scoped class to component. I'm going to say that I'm going only to be able to reference state machines that are in the same package. So the effect of the pattern application is that when I have this file, this architecture, I'm going to be able to reference this state machine because it's in the same package, but I'm going to be able to select this SMT2 state machine. So the other pattern that we define is the visibility pattern, which allows which subset of elements to expose to other fragments. So in this sense, we can attach this visibility pattern to any class, and we can say that they define also the scope and also an OCL constraints, in the sense that we define the visibility for workspace, for project, for root, and for package. In this example, we say that the scoped class component, we also apply this to component and the reference state. And now we say that the visibility is going to see that the same packet that the is public should be true and don't start with the underscore the name. So now the effect of the pattern is like I'm not going to be able to reference this object because this name starts with 2 underscores, right? Because this element is not visible. So the other pattern is the indexing pattern, and this pattern is basically to speed up the computation of queries by creating indices. So usually you have a relation between the constraints that you have attached to your meta model and the indices. So in this case, this is the meta model from the indexing pattern, and you can instantiate it to any class and instantiate it to any attribute. Right? In this case, we use also a state machine, and we instantiated, we indexed the M name with a string. Also, it will be very beneficial if you use this these constraints. Okay, so the other pattern that we have is the scoped validation pattern. And this is that we usually have our meta model and OCL constraints that are usually evaluated on monolithic models. But now that we have our meta model fragmented, it is natural to incorporate the notion of the scope. So in this sense, we can apply this this constraint class, and we should define the name statement as an OCL expression, and we can give also an error statement to give some feedback to the user. So we can define the scope. Of course, this is also based on the fragmentation pattern. I would say that we can execute a constraint in the same workspace because if it's a global, so it's a time-consuming constraint, so we need the whole workspace or the whole project, the same root package, the same package, or maybe these constraints only need to be executed in the same unit. It would be very beneficial for us because we didn't need to load the whole model. So this is the constraints that we applied for the import class. And yes, we define like the name, the statement, and we say that the scope will be the same package. Okay. So for the scope validation, we define 2 scenarios, which is the incremental and full validation scenario. So the full validation is very useful because probably you are loading basically the first time your project, and you need to, for instance, to execute all the constraints to validate if this project is correct. But sometimes you are working on the project and you're working with the file or even with the package. So you need to load other models to get a good to execute in a good way your constraints. So you're working is this F1 file. So probably these constraints is going to execute it in the package, but there is no need to load this other package to see if this whole model is correct. Okay, so all of these patterns and the modularity pattern are included in this tool that we call it EMF-Splitter. And basically this tool, but it has some a set of wizards in the sense that you can define those patterns very easily. And in this example, we say that we select this modularity pattern for WT meta model. Say that in the first view, you have to select the root of the root project. And in the second page of this wizard, you can select also which class is going to be the package and which classes are going to be the unit, and to fulfill also the other information that your icon or your extension. So when you use this wizard, what you get is an environment in which you basic on EMF in Eclipse, that in EMF you by default has these 3 editors, and you start creating your model in the fragmented way. Right? So now it would be desirable to have attached to this environment a graphical environment for model creation, in the sense that you have several editors to help the user to create these elements. So for doing this, we have this. We're going to talk now about how to define the graphical concrete systems, and we're going to propose some heuristics to assist in the graphical concrete systems creation, and a read-only representation style for collections. After this, we see how we can combine this graphical representation with the fragmented model and the tool support we're going to present also that we call EMF-Stencil, that is compatible with the EMF-Splitter. So usually when you define your meta model and you would like to have your graphical concrete system, you decide this is an ad hoc process in which you have your meta model and you create a map between the classes and shapes or icons, graphical elements. Like in this sense, we have like a state machine. This is a square. Initial state is a circle with black background. Simple state and the edge is an arrow. So we create this graphical editor that we're going to create models that are conforms to this meta model. So what we're going to propose here is in this ad hoc process, the use of heuristic and the read-only representation style for collections. So to do this, we create an intermediate meta model to represent the graphical concrete system in a neutral form. So we call this meta model graphic representation. And this meta model basically supports the creation of layers, the creation of graphical elements, is node-like or edge-like. You can also define spatial relations, say that one element contains an other element, or an overlapping, which means that the element should be very close in the border of another element. And also you can create a representation style for collection, which basically resembles statements of general purpose languages. So we propose a set of heuristic in the sense that when we have our meta model and create our concrete system, we first start with the root. The root basically is the canvas. It's going to represent the canvas in which we're going to insert the rest of the elements. So one of the root strategy it would be to select the class that contains more classes, and also the class that contains with no parents. That would be because it makes sense that we have a class that are going to contain the rest of the elements. It doesn't make sense that you have some elements that are outside of your model. And the other strategy is to use it with the modularity pattern. If we know that there's a modularity pattern instantiated, we're going to say that we're going to create a visualization for each unit. Due to the units are the ones to group the rest of the elements. So the other strategy is to use arc strategy, which we have two strategies: the simple direction strategy, in which we select, we have a class, and if this class has exactly two references 0 to 1 that are not contained, so we'd say that this is an arc class. And also we can basically select the arc class based on the parameter direction arc strategy, because usually we use naming convention like source, target, and we can use this naming convention to automatically define these references. So the other strategy is the label selection. And we say that usually if you have an object and you put in a name, we say that we can select the first string attribute of this class. We say that we can select the identifier of the class. Say that you have a class that have an ID, Or we can say we just also parameter string attribute that is basically we get benefit for the naming convention because usually you put name as an attribute of ID. So we can use this information to automatically select this label. The other strategy are the container reference representation, because we say that if we have a class that contains another class, we say that it is an affixed, or maybe it could be like a compartment class, or maybe you want to select it as a link. And the last heuristic is the graphical style, which is basically divided by two. Say like you can select a shape, you can select an icon. So if you select like shape, you say like you can use the semiotic clarity, which is one of the principles of Moody that said that that there should be a one-to-one correspondence between the classes and the graphical symbols, which makes sense. So, and you also can select the random. So, so finally, you can also get benefits with some services like to get an icon. We implemented the Pixabay and the Google, and we retrieve some icons based on a query that gets an icon based on the name of the class. So, as a complement to this heuristic, we propose a read-only representation style for collections, in the sense that we provide presentation for visualization of typical graph structures. And we identify 4 styles, like when you have a loop, when you have a tree, a condition, or a linked list. I'm going to explain that when you would like to have like a linked list, let's say that you have a class A that reference a class B, and what we would like to get is this representation, in which you get like a list of all elements, right? So you should have to tag this class A as a node type and this class B as a containment. And our framework is able to generate all this infrastructure that you can basically through a wizard can customize at your need. So how we can join this graphical fragmented model with our graphical representation? So by applying the fragmentation pattern for the creation of model, different files are created in the hierarchical structure. So that is mapped to the file system. So the fragmentation strategy relies on the use of cross-references by which object can refer to other objects that are in other files. But these cross-references can be container references or cross-references, in the sense that in the WT components has the container reference to the graphic system, and when I reference this component to this state machine is a cross-reference. So then using the mechanism of diagram can also be constructed in the fragmented way. So in this approach, the object annotated with units are those that group all the elements, so in the same file. So we allow the creation of diagram for each of them. So this is the figure that we can be able to create a diagram for represent the state machines and also to represent the different components. So we created a tool that we call it EMF-Stencil. And EMF-Stencil basically has also wizards in which you can define, in which you can customize your graphical editor, also have the creation of representation style. And in the second page, you can define also the shape, the width, the color, and so on and so forth. So currently, we support Sirius as a target platform. And this is an example of a running example of wind turbines. You have this editor for the creation of your state machines, and has this other editor for the creation of the component. So using our approach, we created other case studies. So for instance, we use it with GAIX. The GAIX is a neutral data format to represent the hierarchical structure of production systems. And also with hashing, which is a tool to create in-place transformation. So if anyone are curious about it, you can, let's see. You can take a look to this GitHub repository, which is in my, that I have in my profile, and we create, this, we share a couple of environment, the scalable environment, like these guys, this Krala environment for the design of structure and architecture-centric cloud robotics, and this very cute example of my turbines, my storm robot editor. So, okay. So in this talk, I just presented a systematic approach to develop a scalable monolithic environment and for DSMLs, and we introduced basically 5 patterns like model fragmentation, reference scoping, object visibility, indexing, and scope validation, and which the tool support EMF-Splitter. And we also present an approach to facilitate the generation of graphical editor, which we implement a set of heuristics and some read-only representation style calculation to assist the user in the creation of graphical editors. And we have our tool support, which is EMF-Stencil. So thank you so much for your attention. So if you have any questions.
Thank you, Antonio, for the nice talk. Is there any question you would like to ask Antonio?
Hi, Antonio. I have a question for you. This is Luca speaking.
Hi.
So my question is about your DSL for the graphical concrete syntax. Is also, my question is to know if it is also suitable for animation. To define animations on the models. And even more challenging question: have you ever thought about extending this DSL for dealing with 3D notation? So that you can deal with 3D geospatial constraints or visualization, because there are some domains where, for example, more advanced graphical concrete syntax can be very helpful, but so far as I know, the tool support graphical notations by Eclipse it's quite poor because it's 2D.
It's 2?
If it has only two dimensions. It's not 3D.
It's only 2 dimension. Okay. Well, no, this is no support for 3D so far. We just support this tool using Sirius. And yeah, that's basically what we support so far. So, yeah. And in the sense, what you mean, animation is simulation?
For example, imagine that you have an executable model for debugging, and then you execute the model, and then you have, I don't know, red or green or yellow surroundings to the icon. That change during the model execution. Can you support this execution?
No.
Define this kind of stuff.
No, I would say no.
Okay.
No, I would say no. We have some kind of, as far as I remember, what you have is you can define like it's not filter, is customize your figure. It depends on the few attributes. You can do that, yeah. But no more, I would say. In the sense that if an attribute is 1, you can put the color like green. If the attribute is 2, you can put the color as blue. Yeah, you can do that with the wizard. Yeah, but I would say no more. Yeah.
Okay.
We have another question by Kurat on the chat. Kurat, would you like to ask, or I can read? But I can read it. Is the index pattern that you have mentioned specified by the user? Selecting which fields to be indexed.
Yes. this pattern should be specified by the user. And what usually you will like is to have some integrity constraints that are related with your indices, in the sense that if you know that you have a query that looks for a name or look for a certain attribute, maybe what you would like to have is an index in these attributes in order to retrieve those elements faster. Yes, there's no mechanism so far to extract information, for instance, for the integrity constraints in order to give to the user a definition of which indexes will be beneficial for the constraints. Yeah.
Yeah, that was my follow-up question. So would it be feasible to do that? We would need to do static analysis, no, of a given query or an operation that is going to be executed, right?
Yeah, it will be at least beneficial for users in the sense that you can have at least an approach of which attributes you are using most, and using this information of reading these constraints, you can get this this automation, yeah, of indices. Yeah.
Any other comment or question you would like to ask? Maybe I can ask you some other questions, perhaps in relation with other, with the topics of other ESRs that are listening, because you have explained one of your techniques is based on fragmentation, right? So you take a DSL meta model, you apply the pattern, and then the model is fragmented. But your main goal here is to be scalable for modeling, so that the user receives an editor that, out of the box, support these fragmentation strategies. So modeling is more scalable. But would this fragmentation have also benefits for the scalability, let's say, of the execution of model transformations, code generators, and so on? Do you think it would lead to more efficient execution of model transformations in some cases? Or would you need different strategies for fragmentation? What is your intuition here?
I would say so, that in the sense of model transformation, if we are able to define which elements have to change, and yeah, it will be possible just to transform the part of the elements that you change into your target model, right? And for large models, it will be beneficial because you don't need to transform the model again, just a part of the model that change, that you change. Yeah.
Yeah, exactly. So
it will be like.
Yeah. Sorry.
No, that it will be like a good research topic to continue with.
Yeah. So I guess you are envisioning here a kind of lazy loading only the fragment that is affected by the transformation, but also because you have fragmentation already, you could do perhaps the transformation in parallel or in a distributed way as well, no? So that could also.
Yeah. And you can also thinking that you can just say, like, for certain files, those are, for example, thinking of ATL, saying that for this file, those are the rules that apply to this file, and maybe we can convert, and there is no need to apply also the other rules because they are not necessary in this sense. Like the same approach that we use with the constraints probably can be used in with the execution of the rules, for example, the ATL. Yeah.
All right. Any other question? Yeah, we have one question by Jan. maybe you would like to ask it.
Yeah. Can you hear me? Yeah. My question is, how does that fragmentation work out in practice? So when I imagine that being used in and I move one element from one
Sorry, I
package to
cannot
another.
hear you well.
Okay. Let me see whether my settings are all right. Okay. Is it better?
Now it's better.
Okay.
Yeah.
How does it work in practice with the fragmentation from a user's perspective? So if I move one element in Sirius from one package to another package, and then according to your rules, some of the links may break because they refer to things in the old package. How does that work out in practice?
Yeah, in a moment we joined this tool with the tool that called it Concordance, and Concordance was the tool developed by the University of York by Dimitris. That basically you can have like a database, an H2 database, I would say, and you have all your references, indexes in this database. So what you will have is when you move an element to another folder or project or whatever, you're able to automatically adapt these cross references to the new, for example, location, right? In this sense, for example, this WT turbine, you have like, I don't know, this WT components, and you have a subsystem. And if you move subsystem from subsystem, at least the proxy cross references that are pointed to this folder, you can change it automatically if you move this file to another folder. I don't know if it makes sense to you.
Yeah, it does. Thank you.
All right. We have another question by Eugene. Eugene, would you like to ask it yourself, or shall I read it?
I can ask it. It's okay. Just a quick question on your thoughts to automatically generate perhaps a default graphical concrete syntax for any meta model, because from experience, especially with Eclipse tools, it is quite tedious to write these, to specify these concrete syntaxes. There's a lot of hooks you have to go through, and it really helps to start from example, especially for novice users with these technologies. So have you thought maybe to help the user by generating perhaps it recognizes, for example, you have a linked list. Well, it will generate something for the linked list for that part. It has, I don't know, a containment. It will generate something for the containment, something generic. So just a question like that.
Yeah, that was the idea when we decided the heuristics, in the sense that you can define or select or read the meta model information, and when you have, you know, the containment, you can say that it's a compartment visualization, and so on and so forth. So yeah, you can basically generate very basic default editor from scratch. Just given the next, you could get a new one. But it would be more difficult for, I would say, generate, for example, or to automate, for example, the read-only collections, right? The loop or the tree, and we only let it in these heuristics that you can customize a bit, and you can customize this heuristic, and you can get automatically this editor. Yeah.
Cool. I'm afraid we would need to stop here. We don't have more time, but at the end of these three presentations, we have half an hour that we can spend for additional discussions. So thanks a lot, Antonio. Nice presentation.
Thank you
let's move
for the
to
invitation.